everyone. My name is Erez Levi, and I'm a founding engineer at Groundcover. And today, I'll give you a fresh perspective on key value stores using eBPF. When working on large-scale systems, tracing issues is not always easy. I'm sure at least some of you have experienced the feeling of staring at a screen on a Thursday evening thinking, what the hell is going on? I want to share with you a simplified version of a problem we had with one of our applications, fetching cached user data. Our application was deployed as a replica set, having hundreds of instances, calling a Redis with millions of keys, and we had an ELB in front of it. Sounds simple, right? Everything went great. Till one day, we started noticing that some of our requests are experiencing higher latency on our load balancer metrics. We needed to find a few needles in a very big haystack. We started looking into tools to help us with the investigation. We already had Grafana in the cluster, so we decided to try the Grafana Redis dashboard using the Redis data source. It was very easy to set it up. Quickly, we got resource metrics, node configurations, command statistics, and slow command log, all fetched from the Redis server itself. But something was still missing. That Redis server was receiving calls from different applications, executing different commands. Where do we even start looking? We needed to find the context of those commands. So we started looking into tracing solutions and quickly discovered OpenTelemetry. OpenTelemetry is an open source observability framework for collecting and transforming telemetry data. To use OpenTelemetry, as some of you know, we need the OpenTelemetry collector. The OpenTelemetry collector receives, processes, and exports telemetry data to tools like Jaeger and Prometheus. We deployed the OpenTelemetry collector as a daemon set next to our application. The daemon set collector was connected to a collector gateway, and the collector gateway was connected to a Jaeger backend. Now that we had the infrastructure in place, we needed to implement the SDK in our application. We added the OpenTelemetry tracing hook with the GoRedis client and injected span context to every Redis call in our application. Once we're done with all the code changes, we deployed the new version. So now we got the spans to work, and we had a lot of spans, and we needed sampling. OpenTelemetry supports both head and tail-based sampling. Head-based sampling means that the decision to sample happens as soon as possible, even the request is not completed yet, while tail-based sampling enables tail-based sampling needs to happen at the end of the process, only after all the spans of that request have been completed. We needed tail-based sampling in order to sample by latency. That's where things didn't go as planned. Tail-based sampling will require 100% of the spans to reach a collector. Sending those spans at that volume has a big negative impact on the pod resource usage. Both CPU and memory went up dramatically, directly increasing costs and degrading performance. Also, implementing the OpenTelemetry SDK in our application and injecting span context to every usage while maintaining version compatibility definitely hurts usability. In its solution, we had to make compromises. With Redis dashboard, we compromised on context. With OpenTelemetry, we compromised on cost, usability, and performance. There must be a better way, right? So what do? Any guesses? We use eBPF. Extended Berkeley Packet Filter, also known as eBPF, is a sandbox environment that allows running programs in the kernel without changing kernel source code or loading modules. What it means for us is that we can safely run eBPF programs as hooks to system call operations. That's a very cool technology, but how can we use it for tracing? eBPF agents typically run as daemon sets and write to a backend. They can sniff network packets, access process memory, detect exceptions and exit codes, and so much more. Let's see how they can help us find the missing piece of our puzzle. In this example, we'll focus on TCP sockets. Every TCP socket has a file descriptor and a port. eBPF agents can use that file descriptor to identify that socket until that socket is closed. We attached probes called K-probes to the core system calls on a TCP connection lifecycle. Those probes can then reveal the arguments that are passed to each system call. The first probes we're going to use will be attached to the connect and close system calls. The connect will reveal the address of the target, as well as let us know that a new connection was created. The close system call will let us know that this socket is no longer relevant. We'll need 2 additional probes for the read and write system calls. Those calls will reveal their buffers and written size. And once we have those buffers, we can continue to parsing their content. We parse the buffers according to Redis protocol spec. Every buffer can have between 0 to n full request or responses. And every request or response end with the delimiter \r\n. Also, Redis uses a type indicator on every response to notify about the type that's about to come. Lastly, we can measure the latency between the first read and the last write until we reach the response end delimiter, which, as you know, is \r\n. Since eBPF agents are out of band, they can trace and sample smarter at the node without changing or compromising the application. In this solution, we compromised on many things, but now it's time to evolve. No more code changes, no more performance issues, and this is what it's going to look like. Now back to our problem. Sorry. We grouped the latency of the Redis calls fetched by our eBPF agent and discovered that some of the nodes were having much higher latency than the P50 in the cluster. We checked the CPU of the pods on those nodes and discovered that some of the pods were unable to reach their CPU limits. We came to the conclusion that it was a noisy neighbor problem. So we drained the nodes, replaced them, and our latency was back to normal again. Solving the problem was very easy, but only after we had all the data fetched by our very own eBPF agent. eBPF-based APMs are here, and it's time to get involved. Thank you very much. Feel free to contact me on any eBPF articulated subject. Thank you.